Lasers are everywhere and are used in a wide variety of applications. They're found in barcode scanners, DVD players, they're used in medicine, they produce dazzling laser light shows, and of course, they're instrumental in micromanufacturing. The acronym LASER, L-A-S-E-R, stands for light amplification by stimulated emission of radiation. The term was coined by Gordon Gould when he was a student of Professor Charles Townes at the Columbia University in 1957. Lasers exhibit some unique characteristics. First, they're monochromatic, which is to say that they have a single output wavelength, or a pure color with an extremely narrow line width. Depending on the laser type, they can have wavelengths from the ultraviolet through the visible or even in the infrared portion of the electromagnetic spectrum. Wavelength selection is important depending on the material being laser processed. As an example, UV lasers are usually best for drilling and cutting plastics. Lasers are also highly directional, where the beam can be as little as 1 millimeter in diameter and spreads very little over a large distance. In fact, lasers have been bounced off the moon to accurately measure the distance between the moon and the Earth. They're also coherent, where all the waves are exactly in phase with one another. The common components of all lasers consist of, first, an active medium, which can be a gas such as in a carbon dioxide laser, or krypton fluoride, for instance, in an excimer laser, which is used to generate high-power UV pulses. A solid-state laser, on the other hand, has a crystal made of ruby, neodymium-doped yttrium aluminum garlet, or YAG as we call it, or neodymium-doped yttrium lithium fluoride, just to name a few. The gain medium can even be a liquid, although dye lasers are not used in micromanufacturing, and there are several reasons for that. The pumping source or energy input can be electrical, such as an HV discharge in an excimer laser, or it can be optical, using laser diodes to pump, for instance, a YAG or fiber lasers. And lastly, all lasers need an optical feedback, and this consists of a mirror or a high reflector and a partially reflective mirror, and we'll talk much more about that later. Finally, a population inversion is critical sustaining laser operation, where a large number of atoms are in an excited state. Looking at the energy level diagram, an electron is pumped to a highly excited state and transitions to a metastable region. The electron will seek its natural or ground state. However, it must release energy, and it does so in the form of a photon. Now, we have a lot of atoms releasing photons in all directions, and this is called spontaneous emission. This is similar to a black light, which is a UV pump source and a fluorescence dye. The dye absorbs the UV wavelength and emits a visible color in all directions. In lasers, stimulated emission is achieved by the optical cavity. Photons bounce back and forth between the mirrors, and as a photon passes an atom in an excited state, it too emits a photon, creating a cascading or a domino effect. The output coupler, being partially reflective, permits the laser beam to exit the cavity. Now, the chart shows the laser types commonly used in manufacturing. Wavelengths can be anywhere from 193 nanometers in the UV to 10.6 microns in the infrared. Average power is typically in the range of a few watts to a few hundred watts. And laser pulse durations can range anywhere from microseconds all the way down to a few femtoseconds. So thank you for viewing, and stay tuned for future installments on laser applications in micromanufacturing. If you have any questions, or if you want to suggest a future topic on lasers in micromanufacturing, please contact me. Thank you.